Good morning. Thanks for being here. Thanks for your patience. We had a bit of difficulty setting up like the live system for a demo later in this presentation. My name is Wesley, and today I'm going to give a presentation about how to lower the barrier for monitoring your ML systems. Actually, before we start, let's start with a question. Who of you thinks monitoring your ML models is important? Well, that's a lot of you. That's probably also why you're here, because you're interested in it. Then the second question, who of you has ever implemented some kind of ML monitoring before? All right, nice, quite a few hands. A bit less than everyone who is interested. So that's good, then I have the right audience here. Before we continue, let me define monitoring. What I mean with monitoring is any real-time information on how your deployed machine learning model is running in production, like all that information that it entails. That's what I mean with monitoring. But first, let me introduce myself. I'm the lead machine learning engineer at Accelerated. That means I have basically two roles in the company. First of all, I'm responsible for training a group of junior to mid-year machine learning engineers in a year with us to like train them, guide them, help them out with things that they encounter at their clients. And then secondly, I'm also doing consultancy projects myself, and currently I'm at a computer vision project at Port of Rotterdam, where I'm actually right now implementing monitoring for that project, so that's actually nice. Alright, why monitoring? Regardless of how experienced you are, what kind of systems you build, it is guaranteed when we develop software that there will problems that occur. And it is important to identify them early. Like if the whole system shuts down, you probably notice quite quickly. But if there's like smaller bugs creeping into your system, you wanna like be able to identify them, and you wanna diagnose like why is this happening so that you can solve it. And then also, if you're able to do this, then you're building up this big database of how your model performed like over the past months, over the past year, so that you can do all kinds of analysis and performance reviews to also improve the way your ML system is working. So now that we know why we want to monitor, we can actually look at how we can do monitoring. And there's quite a lot of tools out there in the open. And today I want to introduce two of them. They are Prometheus and Grafana. Who of you have worked with this before? Nice, also quite a lot of you. So just to quickly introduce them, Prometheus, I see this as like the back end for like monitoring and alerting. It's used like a lot. It's like this big open source tool. It's used for like traditional software monitoring stuff. It can be used for ML stuff, but it's maybe not that popular yet. It works with a time series database with a smart data model that it can save data in an efficient way. It works with this HTTP pool model. That means that if you have your own model deployed as an API somewhere, you just need to expose the metrics, and then Prometheus will scrape them and takes care of the rest. Also, they have this PromQL querying language where you can aggregate and do all kinds of queries on these metrics. And then secondly, there's Grafana, which is this dashboarding tool. Probably a lot of you have seen it or used it. It's used for interactive visualization. It's kind of this front end on the monitoring system, and it has a nice integration with Prometheus. It looks a bit like this if you spent a lot of time building nice dashboards. Then let me introduce a scenario. So let's say we do a project and we're trying to predict churn for like this company. Doesn't really matter what company. We're trying to predict churn when like people will cancel their subscription. And you've built a simple decision tree model on a specific data set to predict for that, and now you're ready to deploy it. And you deploy it using a fast API app. You expose the endpoint and you just send a post request with your feature values, and then you get back like either this client is going to churn, yes or no, within a given time frame, let's say a month. You actually implement two endpoints, one as a dummy with like a random endpoint that just gives you some random prediction back, and you actually implement your model on one of the other endpoints. And then besides that, we have our two interesting tools to do monitoring, Prometheus and Grafana. And I'm going to run through this scenario for my talk, and then in the end give you a live demo of how it might work in practice. To actually set us up locally, I have a bit of code here on the slide. It's not about reading all the details of the code. I basically want to show you that if you want to run this locally, you can do this by getting 3 parts in your Docker Compose. Top part is your fast API model. It runs on port 5000 in my case. Then I have Prometheus. I just use one of the available versions that's on Docker Hub, and I use Grafana. So we have these 3 things. By the way, all the code that I'm showing now is available on my GitHub, and you can actually run the same project I'm showing here. You can run it also yourself on your own computer. Later, I'll provide the link at the end. So this whole system with this fast API app, even though there's like this decision tree model like deployed in there, there's like complex data flows, but it's still an application that needs to stay live and needs to be monitored. So we start out from the point of this traditional software monitoring, and Google developed this idea of the 4 golden signals. That's these 4. These are the 4 most important things to monitor if you don't have anything in place already. So we monitor traffic, like the number of requests per second you get to your system. We track latency, like how long does it take to handle such a request. We want to monitor the errors, like either as like an absolute count or as like a percentage of all your requests. And then lastly, there's saturation, which I consider more like an infrastructure monitoring thing. So I'm not sure if I want to include that in my application. You want to include it at your system. So let's actually do that. Let's make it practical. This is the endpoint that we have. It's a fast API endpoint. I assume most of you have seen it. It's basically this function that gets run when you hit this endpoint. So this is the /predict/model endpoint, and what happens when you put a post request here, this piece of code gets executed. Pretty simple. We get the features in from a JSON, we parse it such that is an NumPy array or a pandas data frame or series, and then we make a prediction and return this prediction. So here it doesn't have any monitoring. If we want to add monitoring, then we do this. We import from the Prometheus client. That's a Python client that is made to interact with Prometheus. We import 2 different objects, the counter object and the histogram object, to basically model 2 of the golden signals. So the first one we see here is a counter object. It's called request count, and it counts the total number of requests. I also put a label name on there so that we can actually distinguish different models, like the random model and the decision tree model that we have later down the line. For the latency, I don't use a counter because we're not just counting stuff, we're actually making this histogram, which is basically a counter of several buckets. Here I just use the default buckets. It's basically just this object that is able to track like how long does it take to fulfill this request. Now we're going to add them to our fast API endpoint. So at the bottom you see the request count. We call the model version and then we increment it by 1. So each time this function gets executed, we increment this metric by 1. And for the latency, we actually use the decorator method. There are just multiple ways of doing this. I want to show both, where we actually calculate the time it takes to execute this function and also track this. Then last step to actually make this a reality is to make these metrics available at your fast API app. Like I said, Prometheus works pool-based, so it's going to look for metrics somewhere on your application and then scrapes them in. So it's the responsibility of the fast API app to show these metrics. And we do this at the /metrics endpoint, and we can simply do that by this generate latest function that we import from this Prometheus client. And then every so many seconds it refreshes and like shows you the latest metrics. You can show it in the demo how it works. Alright, now we've looked at this traditional setup, like we added 2 of these golden signals, but we're here to talk about ML monitoring. So what is it that actually makes this ML monitoring different? Well, there's a few things. First of all, we have data flowing through this system. And there's all kinds of things that can happen when we have data and we want to be aware of it. And I classify them in 2 different categories. There can be problems with data availability, maybe like one of your data sources is offline, or you get it like in a wrong way, and your model or your system is not able to recognize your data. Or we can have problems in the category of quality, that the data is actually available, but the distribution's changed completely. Maybe like the unit of measurement is different. Maybe there's just changing things in society while there's things off. All kinds of things. And besides data, the one component that's different, we also have this black box model that is trained on a specific data set, which is basically a sort of snapshot of capturing these relationships from the data to making predictions. And typically the performance of these models decay over time. Depending on which use case and what industry, it's either decaying fast or it's decaying very slow. But it's kind of a given fact that these models tend to perform worse over time. Alright, so let's actually look at a schematic setup of this machine learning model. Let's say from the left to the right we have 2 input data sources, 1 and 2. From there we engineer the features, they get calculated in the prediction system. So we end up at the features. From there the features are fed into the model, and from there your model makes a prediction. So we have this very simple setup with data flowing from left to right. If we want to add monitoring, first step what we can do is just measure the model output. So we can measure like distributions of what gets predicted, whether it's like a classification model or regression type model or other kind of things. We can just capture whatever is like the model is outputting to answer the question like, what is my model doing? Because the whole idea of this monitoring is like, hey, what is my model doing? So that would be like the first priority of monitoring. Then secondly, to answer the question, how well is my model doing? Is it making the right predictions? We need to know the ground truth. So if we're able to get the ground truth, it would be good to feed that back into the system and actually monitor here the model performance. In this case of churn, we make predictions whether this customer is going to churn within a month. We only get the feedback like 1 month later. Because if we now predict that he will stay, then we actually need to observe this customer staying for like 1 more month, and then we actually know if this was the right decision or not. So there is this delay in actually calculating how well your model is performing, but it's one of the most important things to do. What else can we do? Well, we can monitor the model input, like all the features that we calculate. We can like log them, monitor them in our system, because if there's something wrong, if your model output is wrong, then probably the first question you have is, hey, but what is actually going in my model? So that's like the next best thing that you want to have if you already have these 2 in place. And then if your model output is wrong, and then you see, oh, but my features are also off compared to what I actually expected or what I saw during training, then of course the last step is to also monitor like your raw data, your source data, to see what you actually received and where you actually calculate your features on. So in this system, we're kind of flowing backwards in monitoring priority. You first want to monitor the things that your end user or your customer or your stakeholder sees from your model, and you want to diagnose problems there. And then in order to like analyze what's going wrong, you go more to the left to your source data to actually discover why certain problems occurred. But if you just have little time to implement stuff, I would start at the right and then go left as time progresses. Alright, now I have some practical steps on how to actually implement this, because so far we've looked at this traditional setup. How can we actually implement this if we have a scikit-learn model? Does not necessarily have to be a scikit-learn model. I just took that example since it's like the most popular framework in Python. So let's create an extra metric, response distribution, to model the model output that we create. Here you see that I made these 10 buckets, just like 0.1 every time, to model a distribution ranging from 0 to 1. And we're going to add this to our endpoints that we already seen before. So the only line that's different is the one highlighted here. Before we actually return the prediction, we are going to observe this prediction on the response dist metric that gets sent to this metric endpoint that gets fed into Prometheus. But now we're adding like all these monitoring steps here in this fast API environment, and it would actually be pretty nice if we can somehow incorporate this in this model, in this scikit-learn model. So what if we do this? We have this scikit-learn model. It's just a simple one. It's a decision tree at the end, and it has 2 steps for pre-processing. For the categorical features, I chose a one-hot encoder, and for the numerical features, I chose a simple computer to deal with the missing values. And we can actually take these 2 pre-processing components, change them a little bit to include that they can do this monitoring for us. So how does it actually look like? If I take the one-hot encoder as example, I'm importing it from scikit-learn, the pre-processing module, and then I'm taking this one-hot encoder. I'm sort of assuming that you've all used scikit-learn before and you know how like the fit transform work. If not, please feel free to ask the questions at the end. The transform step is like it's saying like transforming your original input to this one-hot encoded features. We make sure to call the super.transform to do everything that the original one-hot encoder already did, but now we're adding some extra steps. These extra steps are getting the feature names, getting all the categories if the category is new, if we have not seen it before, which of course can be the case in this one-hot encoding example. Then we'll see it show up as none, and then basically we loop through all these categories, and for each feature, for each category, we increment the counter. So we get like a counter over like all the features and all the possible categories and also the missing ones, and we just count them to see what is actually flowing into the model so that we can monitor it. Then second example, same ID. Here we take the simple imputer, same structure. We take the transform. We make sure to do the super transform, except that we also add the thing. And now we're adding which features are imputed with missing values. So later down the line, we're able to see which features are actually showing up with a lot of missing values so that we can make decisions about it later. All right, let's actually do a demo to show how it looks like in practice. All right, let's start here. You can all see it, right? Yeah. Localhost 5000. So this is my monitoring app, the Fast API app. Is it big enough? I think so. Let's go to the predict/random endpoint, where I just get a sample back from a uniform distribution with some kind of time delay on it. If I just run this a few times, then I can see we get like new counts in. If I then, if I then go here and ask in Prometheus, so this is Prometheus running at localhost 1990. If I go to this request count total and execute it, I've run it before, I can see that this random endpoint has been hit like 8,000 times already. If I like 8,073, if I now hit it a few times again, we can actually see this going up. It takes a bit of time before it gets scraped, but now we see that it has an increase of 3. Actually, instead of like manually hitting this all the time, I actually have a script. So this is where I have my Docker Compose running, and here I can just run the simulate random endpoint, and we're going to hit this endpoint in a while true loop. Let's actually look at the dashboard that I've created for this one. We go to the random endpoint. I just started the simulation. We're looking at the last 5 minutes of data, and we actually see that we now have like an increase in traffic. So this is implemented. I can show it for a bit. This is incremented as the request count total. I filter for which model I'm using, and then I calculate a rate over it to get like the number of requests per second. So we can see it here going up. We can see the error rate also going up. In the simulation I included that sometimes it just fails, so we can see some errors. Here on the right side we can see the latency. You can see like how long it takes to process this request. It has an exponential simulation on that, so like the bright colors are where it's most often, how long it takes most often, but of course there's some distribution. And then here on the bottom we actually see the distribution of the model output show up. It's a uniform distribution, so if we give it enough time we'll see that it converges to this uniform distribution. All from these simple metrics that I actually showed. Then secondly, we have this other endpoint. So let me go back to this code again, and let's run the simulation for the model. So I can simulate model here. I'm going through some production data and just replaying these instances. And then I can switch to this decision tree and we can actually see what happens. We see that the traffic is already increasing since I just started it. We can see the latency starting. We don't see any errors yet because the metric doesn't show up unless you hit it like once. So when we get the first error, then we would actually see it happening here. The way this works, I promised to show that. There's this metrics endpoint on the API. It's not about the details, I just want to show you that like all the metrics are tracked here. So this is what is made available by this fast API app, all these metrics for Prometheus to scrape. And then we just use it to actually show it here in this dashboard. One other thing that I want to show was that we use this one-hot encoder to actually create this metric for all the categories that we are finding in our data. So I have this model categorical total metric which has feature names and categories. So if I execute this, we see actually like a big list of all things that gets counted. Let's make it a bit more visible and just select like one feature. I select feature 0, which is the region feature. Here we can see, if I increase it a bit, that we have like different kind of regions, and here we count like how often we encounter this region in production, which is simply filtering them here. And that's also something that we can actually add to our dashboard. So below here, what I have created, we have 3 categorical features. So for feature 0, 1, and 2, I created this bar chart where we can actually see like, hey, how many times did we see this category, and do we observe any weird things? Well, weird thing I observe is that like most of the API calls actually have none as value for this region. Might be that just the case that this data works this way, it just recorded like this, or maybe there's something else happening. It's at least good to know that we're aware now, and then we can figure out what to do with it later. Same thing here for this one. And then second transformer that we changed in scikit-learn was this simple imputer. And here we can see, well, these are the categories numbered, so they don't have the name here. We lost them, could add them later, but for now it's just numbers. We can see like how many missing values are actually imputed. So feature 10 and feature 9 are the ones who have like crazy high number of missing values. Here it's just absolute counts, but you can of course also make it a ratio of like total number of requests. And every time like you change like your time frame, like the dashboard updates and recalculates like for this time frame how many actual counts or ratios or things you saw. Alright, that was the live demo part. Let's continue for a little bit to talk about model decay, because now we have seen a few things that we can track and that we can actually use to understand what our model is doing. But like I said, the model decays over time. Like it's not guaranteed to give you this stable performance, and it's often decaying or getting worse over time due to drifting distributions. And there's basically 3 types of drift that I want to introduce. First one is data drift, then we have concept drift, and then we have the train surf skew, which is maybe not actually a drift, but it fits this explanation, so I just include it. Data drift is the case when the input distributions actually change. So right from the source, your data just looks different, like a lot different or slightly different, but at least meaningful different, such that it is reflecting any kind of changes in the underlying data. There's ways to actually compare distributions. There's like this KL divergence, or there's other kind of ways to compare them mathematically. But already from looking at the distributions in your like production system and looking at what you had during training can already be insightful before adding this complex logic. So data drift is like inputs are changing. Then we have concept drift, which is actually the thing if the learned relationships in your model are no longer true. So you might have the same input data, then your model makes the same prediction as it always did, but something changed in reality, and your model should now, because of some reason, should predict something else. Maybe things in society changed, maybe a pandemic hit it, and a lot changed. So we need to recalibrate this model, and we're not going to find that if we just look at input distributions. We are actually only able to find it if we can close this feedback loop and see where your model starts to deviate from this ground truth. Like it says here on the slide, it needs to have white true in production. And from there we can actually measure like accuracy or mean absolute error or whatever metric you use to train your model and to evaluate your model. You can do it in production too, given that you have this data. And lastly, we have this train surfing skew, which is actually the mismatch between train and production phase. This can have like multiple causes. There can either be a time gap between the moment you train, then you have like data that's maybe a few months old, you took it like a sample, and then actually when you use it for production, something changes. There's like a reason why it's not adding up, and it's basically just your training data not generalizing to your current case. And the same way you deal with it, you compare these distributions on metric, either as a human interpreting it or adding like all kinds of algorithms on it to compare these distributions and put thresholds and put alerts on your Prometheus system such that you get like a notification when something is like meaningfully different. And this thing also gives us like some kind of notion on the question like, should we retrain? I think it's always important for us as the person who creates this model to make a conscious decision about it and not just blindly retrain and hope that now everything is solved. But at least it gives us information to make this decision on. Alright, now wrapping up, I've taught you a lot about like the concept of modeling machine learning in production. I've showed you some practical things, I've showed you this demo, but I think the most important thing to actually recap is the priority of adding stuff to your model. First thing, if you don't have any monitoring, please first add the golden signals to get like an idea of the general status of your application. Is it running? Is it getting errors? What is the time that it takes for these requests to process? Gives you a lot of information without actually diving into ML. Then it's about your model output. Your model is the core thing of what you're presenting to your user. So if you model the output, you can already have some guesses about whether something's going wrong or not. Then next big step is to add feedback. Can be difficult to do, but will be really valuable to measure actual performance of how your model is doing, and it allows you to identify concept drift. Then fourth step, add your training data into Prometheus so that you can directly compare distributions of your features and your source data and like production and training so that you can discover this training surfing skew. And lastly, add monitoring on the distributions of your features and your input distributions for data availability, data quality, and data drift. And with these things, you are enable yourself to actually find things that are wrong in your ML system and not have your end user come to you and say, hey, like, why is this not working, or why do I get bad results? It's like not the fastest way if your stakeholder or end user has to approach you to tell you that something is wrong while you are making and running this model. All right, perfect timing. Thank you.
All right, thank you very much, and very impressive timing on your talk. Time for a couple questions. So, could you go back to the second learning implementation that you showed? Because I was wondering, you can override the method. Yeah, that's the one.
This one, yeah.
Yeah. So okay, you can override the method and add that information in, which is sensible. But I wonder, is there a reason why you wouldn't want to have that as a separate component inside of learning in your pipeline step? Because if you use this, you have to override every single transform you might want.
Yeah. Depends on like if you need the same thing for every transformer. Like for now, this one-hot encoder, I want to do these categories, but maybe you can like grab this piece out, make it a separate component, and when you're dealing with categories, just add this step. Yeah, could be done.
Is that okay?
Yeah.
But there's not a specific reason why you have to do it this way?
No, I don't think so. No. All right.
Thank you. Really lovely talk. My question is about time. So you showed us a few steps setting up Prometheus and the logging.
Good afternoon, everyone. I know you're all
And then
Duff truck outside. Go check out the Duff truck outside.
right, check out the truck. And then putting.
I would like to let you know. So if you've never been in a truck, go and. Hello, everyone. The Duff truck is open outside. So if you want to go and check it out and see what a truck looks like, go and see it outside. It is an award-winning truck with lots of technology.
Right. So then there's the Grafana dashboard. Could
Yeah.
you make some comments about what takes the most time?
Okay, this is the last time I will say this. The truck is outside, full of technology. If you're very curious to know what a truck is like, go in and see it. It is open. Everyone can go and try it out. Just don't leave too many breadcrumbs inside. Thank you.
All right, let's try to answer your question. When I started with monitoring, I first started to create this local setup with this like Docker Compose that I showed earlier, and basically getting like a basic system running with this like example project and this decision tree. I got it running in like 1 or 2 days. If you want to add this to like a more serious like production setting, you probably want to deploy this on Kubernetes, and takes a little bit more time. Currently, I'm doing that at Port of Rotterdam, and like we've spent now like 1 or 2 weeks on it to just like set up all the components, make sure it all works. Yeah.
Hi, thanks. So you also talked about the feedback, so comparing the predictions to the actual ground truth.
Yeah.
Does the Prometheus support this in some way? Because you'll have to like recall your model at some point in the future with the same input data.
I wouldn't recall the model. What I would do is like somewhere have like a database, maybe SQL, maybe Redis, somewhere to store your actual predictions that you make. So you have like your, when you do this post request with your data, you want to save like all your features. You want to save like with which model you make a prediction and what the prediction is. And then later, like a month later, when you get this information available on this specific ID, you want to add your ground truth. Then you just build yourself a database with like all the values, the predictions, and the ground truth. And then you can expose that in Prometheus to do all kinds of queries on like confusion matrices, how many true positives do I have, those kind of things. So I would keep it outside Prometheus until you know everything.
Maybe one more.
Thank you. How would you monitor the performance of a computer vision model, for example?
Yeah.
Because
so
those are quite hard to get
Yeah,
the
that's
label
actually
for?
what I'm currently doing. So great question. At Port of Rotterdam, we're doing this computer vision model for asset management. It means we have like a variety of different models. First of all, we have an object detection and segmentation model to just identify things like lampposts and traffic signs and those kind of things. There we put counters on, and you can also, like, if you have a validated data set with like IOUs, you can sort of like calculate like how much percent of your mass that your model creates is actually also in the ground truth, to like get some idea of the performance of these models. Of course, for like production data, you don't have drawn all these mass, so you don't know it, so you can just count and see like if it makes sense, the amount of things that you detect compared to what your inputs are. Secondly, we have a number of image classification models running to classify the quality of these kind of things. Like traffic signs, they can be broken, they can be dented, they can be like less visible. We have created some models to actually identify those, and that's just like a classification model. So the same thing that you can put on a decision tree, you can put on this classification model, because there's just ground truths and there's predictions.
All right, thank you very much. Let's give a hand for our speaker again.
Thank you. So if you want to play yourself with this project, it's available on my GitHub. I will also upload the presentation. You can basically do the entire thing yourself and extend it. Thank you. No, it's not.